Hello. Today, I'm here to talk to you about the work done with my colleagues at the University of Toronto on memory management and elastic system software stacks. Traditional data center provisioning has its hands tied. For example, with the traditional working set model, an application must have its working set in memory to avoid thrashing. Therefore, we must allocate an application to account for its peak working set if we care about performance. However, this also means that outside of the peak memory usage, most of the allocated memory is not utilized. On the other hand, today we see new elastic applications break these old traditions. An elastic application practically never stops benefiting from additional memory while still being able to make progress given less memory. In the figure, we see two Spark jobs, k-means on the left and PageRank on the right. We can see that as the heap size keeps increasing along the x-axis, the job completion time drops significantly along the y-axis. As more and more data fits in memory, we see a decrease in the time Spark spends managing memory, shown by the green bar. This creates an interesting opportunity. If we can provide these elastic applications with more memory, we can improve their throughput. But how do we get them more memory? Well, we want to dynamically adjust application memory usage to match physical memory availability. We could try to do this in the OS, but the OS lacks critical domain knowledge about application memory usage. So we want to perform the adjustment directly in the application where all the information is. However, existing memory abstractions greatly hinder application memory management, and this problem only gets worse as complex applications have multiple layers of memory management, each with their own abstraction. So let's walk through an example of the problems created by memory abstractions in each layer of a Spark stack. First, at the very bottom, we have the OS, which abstracts away physical memory. This leads to applications falling back to static settings, such as the JVM heap size, to try and limit their memory usage. By limiting memory usage, these applications attempt to avoid paging, but are completely unable to adapt to changes in both their own memory demands and system memory availability. Next, the JVM further abstracts memory by automatically managing all object allocation and reclamation in its own heap. However, since the heap management is not based on physical memory availability, the JVM becomes opportunistic. To improve performance, it'll delay its GC even if it holds mostly garbage. Additionally, it optimistically holds on to unused heap space on the chance it will be used again later on. This leads to the JVM memory footprint growing to the max heap size without ever returning memory to the OS. The poor OS must assume the JVM requires all of its retained memory. Therefore, when physical memory is exhausted, the OS has no choice but to page. However, a much more efficient solution could have been for the JVM to perform GC and return its unused memory to the OS. Finally, Spark further abstracts memory as it must partition its large input data into smaller blocks. Therefore, it manages a block cache which is statically sized based off of the JVM static heap size. However, the memory management of the block cache happens with absolutely no coordination with the JVM's GC. For example, the JVM may wish to perform GC, but as long as Spark holds on to memory, the JVM's efforts will be wasted as it finds no garbage. Spark could have simply evicted blocks and continued execution completely fine while still allowing the JVM to reclaim memory. But without coordination, memory management efforts are wasted. Spark could also perform eviction, leaving large amounts of garbage memory in the heap that go completely unutilized. Now, let's look at an actual example of these abstraction problems. In this figure, we have a server running Cassandra and Elasticsearch together. When they run unmodified in the top figure, we see their memory usage continuously grow. Therefore, if we were to provision these applications for their peak usage, we would require over 30 gigabytes of memory. However, the ground truth is that their memory demands are changing, and they are retaining much more memory than necessary. On the bottom figure, we can see that if the applications return memory when it is unneeded, we can accomplish the exact same task in half the memory usage. So to summarize, we've seen that memory abstractions are hindering elastic applications. They lead to static settings that cannot adapt to changes in memory demand or availability. And the problem is only made worse with modern complex applications containing multiple memory abstractions. Therefore, we created M3, whose goal is to improve the throughput and utilization of elastic applications. M3 works by bridging memory abstractions so that the memory management is coordinated and dynamically reacts to changes in memory demand and availability. For the remainder of this talk, we'll discuss the design of M3 before we go over its evaluation results and concluding. To start, in M3, static memory settings are removed, and applications are allowed to continuously allocate more memory. Next, we build a monitor that watches the system's physical memory. When physical memory passes certain thresholds, the monitor sends out a signal to the applications. We use two thresholds that are updated dynamically based on the system's memory demands. The low threshold represents an early warning, where applications should return an excess memory that they've held onto. The high threshold signifies the system is nearing exhaustion and applications should try their best to return memory to the OS. Applications under M3 require two modifications. First, the signal handler must be added to reclaim and return memory on demand. Second, the application must implement the adaptive allocation protocol on its allocation path. The job of the protocol is to slow memory growth when the system is nearing exhaustion, while still allowing applications to grow when memory is available. M3's design is rooted in a practical implementation of the end-to-end argument. The monitor only notifies the applications of memory pressure. It is completely up to the applications how they reclaim and return memory. Furthermore, all decision-making is decentralized, avoiding the need for intrusive changes. To keep modifications simple, existing mechanisms such as GC or cache eviction are utilized for reclamation. Although each layer in the stack must be modified as they all perform memory management, these principles allowed us to only modify up to 250 lines of code at any layer. Now, let's walk through an example of a Spark stack handling a signal from the monitor. On startup, Spark will first register its signal handler. Then, when the monitor detects system memory passing a threshold, it'll send a signal to the process. In this case, the monitor sends a signal to the JVM, which then calls the Spark signal handler. The topmost layer then begins reclamation. In this case, Spark will evict from its block cache. Once reclamation is finished at one layer, it must notify the layer below it. For Spark, it'll call an exposed JVM GC API. Once notified, the next layer performs reclamation. In this case, the JVM will perform a GC cycle. Finally, the lower layer returns the memory back to the OS. For the JVM, it'll use the madvise system call. With this step, memory can be allocated to other processes to avoid paging. Now, let's take a look at the adaptive allocation protocol. The goal of the signal handler was to return memory to the OS, but that is not enough to avoid exhaustion. While memory is being reclaimed and returned, the adaptive allocation protocol must slow down the application's growth. This is done by dynamically adjusting an allowed allocation rate. An allowed allocation is an allocation allowed to grow the application's memory, while a disallowed allocation must first reclaim memory equal to its request before continuing. We can see in this simple code example, a cache can simply evict the same amount of memory as the allocation if it is disallowed. This is very similar behavior to when the cache is at capacity, so there's no correctness issues or complex modifications required. Allocations are allowed based on the application's ability to reclaim memory. Immediately upon receiving a high threshold signal from the monitor, the allow rate is set to 0%, and from there it linearly recovers over time back to 100%. We define an epoch as the time taken to handle a signal, or in other words, the time taken to reclaim and return memory. The user then specifies the number of epochs that must elapse for the allow rate to fully recover back to 100%. This has two important properties. First, it rewards efficient reclamation. Faster signal handling results in smaller epoch times, which leads to a higher allow rate and more memory growth. It is safe to grow these applications as they have shown to promptly return memory back when necessary. Second, application memory demand is respected. An application experiencing high demand will make many allocation requests, which over time will result in more allowed allocations and therefore memory growth. Now, let's revisit the monitor. To maximize memory utilization while still avoiding exhaustion, we dynamically adjust the high and low thresholds so that signals are sent based on the current workload's demand. If applications reclaim memory quickly and the thresholds are too low, memory will be underutilized as the application returns memory before there is any danger. Conversely, if the thresholds are too high, memory may be exhausted if applications do not reclaim memory in time. The low threshold should temper how often the high threshold is reached. Therefore, if we spend too much time above the high threshold, the low threshold should be lowered to reclaim memory earlier. While if we spend too little time above the high threshold, we should raise the low threshold to reclaim less memory and improve utilization. To adjust the high threshold, we define a top of memory and adjust the threshold based on the time spent above and below this top. Now that we've seen M3's design, let's look at how it performs. We set up a cluster of 9 servers, each with 64 gigabytes of system memory and 16 cores. We have 4 jobs. PageRank, NWeight, and K-means are from the high bench suite and run on Spark and the JVM. Additionally, we create a cache and go that runs a mixed read and write benchmark. We create 16 workloads made up of a combination of these 4 jobs with different schedulings. We evaluate M3's performance by comparing the average speedup of each application's completion time. We compare M3 with 4 configurations that increase in how unrealistically well they perform. First, we compare against the default configuration with all parameters left unchanged. Second, we compare against a global optimal configuration. This configuration sets each job's parameters to maximize the average throughput of all 16 workloads. This configuration requires knowledge of all possible job schedulings and extensive testing to tune. Third, we compare against an oracle configuration, where the parameters of each job are tuned individually for each workload. This configuration requires separate parameter tuning for each possible job scheduling, which is completely impractical. Lastly, the Oracle with Spark parameter configuration extends this by also tuning unadvised and highly sensitive Spark parameters. These last 2 configurations produce completely unrealistic results that M3 must compete with, as they require Oracle knowledge and endless tuning to achieve. In this figure, we see the 12 workloads where M3 has an opportunity to improve throughput, and it does just that. Each bar shows M3's speedup over a configuration for a particular workload, and M3 outperforms every configuration in every workload. Even compared to the most unrealistic configuration, the Oracle with Spark configuration, M3 is 1.6 times faster on average and 3.1 times faster in the best case. Compared against the slightly more realistic global optimal configuration, M3 is 1.9 times faster on average and 3.4 times faster in the best case. Now, let's investigate exactly where M3 speedup comes from. This figure shows an unmodified execution of 3 unique jobs started 180 seconds apart from one another under the Oracle with Spark configuration. The dotted line shows the current physical memory usage, while the solid lines show the memory usage of each job. We can see each application grow to its statically partitioned size and stay there for the remainder of its execution. This leaves large amounts of unutilized memory at the beginning and end of the workload where the job's executions do not overlap. Now, let's look at M3. This figure adds in the parts of the monitor. The top is shown as a solid line at the physical memory limit, while the thresholds are shown as the dashed lines. The orange dots signify that applications are receiving a low threshold signal, while an X signifies a high threshold signal. unlike the unmodified version, we see the first job aggressively utilize the available memory at the beginning. Once the second job starts, the first job begins to receive signals and returns its memory, which the second job promptly allocates. Here, we can see M3 balancing memory as the demand of the second job allows it to grow while the first job shrinks. By being able to utilize all this memory, the first job finishes significantly faster than in the unmodified version. This in turn allows the second and third job to operate at much higher memory levels as the first job is out of the way. In the end, all three jobs finish significantly faster under M3. Now, let's look at M3's worst case. This occurs when there are no changes in memory demand or availability, and static settings are able to achieve ideal performance. We created workloads running identical jobs that all start together. Despite having no opportunity to improve performance, M3 is still only 7% slower in the worst case and 3.8% slower on average compared to the Oracle with Spark configuration. Despite performing well, M3 comes with some limitations. Due to its practicality and decentralized nature, M3 cannot guarantee that its memory distribution is optimal. Additionally, it also requires developers to faithfully implement the policies we have outlined into their application. M3 cannot handle a malicious application that holds on to unused memory and starves others. Over the years, there have been many works attempting to distribute memory and coordinate memory management. M3's uniqueness comes from its combination of crossing every memory abstraction layer in a complex elastic software stack, while also following an end-to-end design, leaving all policy to the application, and finally, its practicality. In conclusion, elastic applications suffer from memory abstractions as their performance is limited by uncoordinated memory management and static settings. We've created M3 to bridge multiple abstraction layers to coordinate memory management and dynamically react to changes in memory demand. We've open sourced all of our work on GitHub, and I'd like to thank you for your time.